Okay, folks, let's look at one more example of a problem, a 4.1 style problem. So finding minimums or maximums, which you call extreme values. All right. The reason why I want to do this one is because of sort of a domain issue. So in other words, what is valid as a potential minimum, what's valid as a potential maximum, and so forth. What's invalid. Okay, so as I did in the previous example, remember, ultimately we're going to take a derivative and look for critical numbers. And there's two types of critical numbers. If a derivative is equal to 0, then you've got a potential for a maximum, because you could have a flat graph right there. You have a potential for a minimum, right? So you don't know that until you look for increasing and decreasing. But you've got potential if you've got a derivative of 0. Not necessarily a max or a min, though, right? We've got those points that we keep looking at right there where we level off for a moment. However, we had other types of critical numbers. So in the previous example, we saw that the function was defined at a certain value, but the derivative was undefined. And if the derivative is not defined at a value, you can say that the function is not differentiable at that value. And what we saw was that that value might be a kind of a sharp little, what we call a cusp or something like that, where the derivative doesn't exist there because I can't really talk about a tangent line there. However, I think we'd all agree that that looks like a minimum, right? It's the lowest point in its neighborhood, so it satisfies our definition of a minimum. Okay, so this example it's similar in the sense that the derivative is going to be undefined at a particular value. So it's similar to the previous example if you watch that video. However, it's going to be different because the actual function's also undefined there. In other words, let's jump in and look at the domain of our original function. Okay, the domain of f. And top is a polynomial, so top is okay, but the bottom, x squared, we know we can't divide by 0, so x cannot be 0 here. So I got negative infinity to 0, union 0 to infinity. Okay, that means, and I'm not even talking about the derivative yet, but this means f of 0 does not exist. The function doesn't exist when x is 0. That would be the y-intercept. So this function has no y-intercept. It exists to the right of the y-axis. It exists to the left, but it doesn't. It just ceases to exist, right? It's on one side, and then all of a sudden it's on the other. Doesn't cross though. Usually I just write DNE, but I'm trying to emphasize that it does not exist, not there. Okay, so good. Let's move on though. Let's tackle this problem like we normally would. So I want to find mins and maxes, so I want to find the first derivative. That's always our step. So f prime of x. And actually, this is a fun one. I'm going to find the derivative two different ways, and then you guys tell me. I might show a third way that you could do it, but I don't want to go that way. But after I do it two ways, you tell me which you like more. So first, this looks like a quotient. So let me jump in and use the quotient rule. Okay, my quotient rule is g f prime minus f g prime over g squared, where f is the top and g is the bottom. Okay, and so I've emphasized in the past that if you want to rename your function something, you can. Let me just disregard that and just plug, without doing all the work on the side, let me just try to dive in. Let me think of this bottom times the derivative of the top and so forth, right? Some people just call it that. So g, so I got my bottom, x squared. Let me wrap these all in parentheses, times the derivative of the top is 4x cubed plus 0, so just 4x cubed, okay? None of those parentheses are necessary, but they're not harmful either. So I had gf prime minus the original top, x to the 4th plus 1. These parentheses are necessary now because of that plus sign. So when in doubt, just use them everywhere. Times g prime is the derivative of my bottom, which is going to give me a 2x. Okay? And all over the denominator squared, which is x squared squared, if we want to show it in that detail. Okay? There we go. That's our derivative. But now, of course, we want to clean that up. So x squared squared is going to give me x to the 4th. I'm multiplying those exponents, right? Not necessarily adding them. The reason why I'm multiplying there is because x squared, what if I had x squared cubed? So let's just check that out for a second. X squared cubed, just as a little aside right here, if you are fine with exponents, fast forward a minute. Here, I claim this is x to the 6. This is x to the 2 times 3. Right? I'm multiplying those exponents, not adding them, and we get x to the 6. Okay? Well, why is that? Well, what is x squared cubed? Is x squared times x squared times x squared, right? And now we're adding these, because this is x times x, so, and then times x, right? So I've got 2 of them and another 2 of them, so 2 plus 2 is 4, times another 2, altogether. I'm adding up, I'm collecting how many I've got. I've got 6 of them, so x to the 6. Anyway, the reason I mentioned that is just because 2 plus 2 is 4, 2 times 2 is 4, so just so we're all clear, it is multiplication, right? Okay, and what's happening up top? Let me clean that up. So here I've got x's, so I can add those exponents, kind of same argument. And then so I've got 4x to the 5th is this term. 4x to the 5th power. And here I have to take this 2x and distribute it onto those guys, and then we're subtracting that. So here 2x to the 5th, right? I'll combine those x's. So minus, let me just squeeze it up here, minus 2x to the 5th. And then 2x times 1 is 2x, but we're subtracting that, so minus 2x. All right, so just squeeze my terms up there for a moment. And now I've got 4x to the 5th minus 2x to the 5th, so I'm left over with the other 2. X to the 5th, and then I've got minus 2x. All over x to the 4th. Okay, so we did our quotient rule, combined our like terms, cleaned it up. Can I clean this up further? Yeah, and actually I want to clean it up a little further. So could I factor out the 2? That's something nice that you might want to do. But then can I go further from there? And there's something else I should do. So I want to pull out the 2, but I've also got a common x up top. So let me pull out a 2x, and then what I'm left with is x to the 4 minus 1. All right. And then my denominator, I have x to the 4, which is really x times the other 3 x's, right? So if I want to pinch off one of those x's right there, 3 of them, the other 1, and the only reason I want to do that is so it looks visually appealing when we cancel those x's, all right? And so what's my final answer here is 2 times x to the 4th minus 1 over x cubed. Okay, cool. So we've got that. So I'm going to clean that up. I'm going to replace what I've got over here. I'll replace the work, and we'll just work with the derivative because that's what we want. All right. So we're in section 4.1. You want to find mins and maxes. We've got the derivative. Just go forward. So we could skip ahead or skip past what I'm about to do. Let me just show something. This comes up sometimes in the earlier sections when we're first learning about quotient rules. Let me approach a second method for finding this derivative. Where maybe I don't want to use a quotient rule, or if I do use one, it'll be like a lot simpler, but I think I can avoid it altogether. I can break that up. F of x, I can split that up as x to the 4th over x squared plus 1 over x squared. I can do that because I've got this simple denominator here, x squared. And then since I'm just adding those terms, now if I wanted to add these, I've got the common denominator, right? So we just add the numerators over the denominator and get it back to here. So that's perfectly legitimate. And now what's the point of doing that is now I can reduce x's. I can cancel some x's. So notice here we can't go ahead and cancel x's right off the bat because of that plus 1. So I'd have to factor stuff out like I did over here, right? I factored an x out and then I can cancel. But I can't factor an x out of this numerator. So I can't cancel everything. However, once I do this, now this term has x's, common x's. And so if I cancel out 2 from the top and the bottom, I'm left with just x squared, right? Over 1 is really what I'm left with. Because what I'm doing is claiming x to the 4th is x squared times x squared over this x squared, canceling like I did above. And so we're just left with a regular old x squared over 1, or just an x squared. In other words, not a quotient. And what do I have over here? 1 over x squared. A couple different ways of tackling this. You could treat it as a quotient, but let me bring this x up top as plus x to the negative 2. Okay? So that's a nice strategy. Do you always want to go that route? Depends. If the bottom is more complicated, like x squared plus any kind of x term plus a constant, then I probably wouldn't do this. What makes me want to do this is since the bottom is just purely x's, then when I break up the top and I can take any pieces with some x's, I can cancel them out. So sometimes if you've got a polynomial over just a pure power function, which is a polynomial, but in other words, if I have a complicated denominator, don't do this. If your denominator is just a power function under a polynomial, you can split them term by term and cancel out a lot of x's. And if this is f, let's see if we can take f prime quick. So that step doesn't really take too long. Now f prime is derivative of, it's just term by term because of the plus sign. X, derivative of x squared is 2x. This is just a little power rule, right? The derivative of this, I'm going to bring the minus 2 down. So I'm going to get minus 2x to the minus 3. And what is 2x to the minus 3? That's 2 over x to the positive 3. 2 over x cubed. And there we go, okay? So is that the same as this? It is. And so what you would want to do now is, so if you use this little shortcut, you get this derivative. Think back to what we did in the previous example, in the previous video, when we took a derivative, we get these two terms. We want to combine those. We want to clean this up as much as possible. So I'm looking at this. So there's still a little extra work. So 2x minus 2 over x cubed, okay? So we just need to get the common denominator here. So I want x cubed is my denominator, so I multiply top by x cubed, and that does it. So now I've got 2x times x cubed is 2x to the fourth minus 2 all over that denominator, x cubed. And now if I pull the 2 out front, I got exactly what we have up there. Okay. So if you like that method, it's sometimes helpful. So again, I'm kind of deviating from the pure lesson of 4.1, which is finding mins and maxes, sort of backtracking into looking at quotients, seeing if are there other ways that we can look at that function and then take its derivative. You know, can we avoid a quotient rule? So a lot of times you can't, sometimes you can. So it's up to you. I mean, if you do it this way that I did in blue, you've got to then get the common denominator, so maybe sort of an extra step, but you avoided the quotient rule, so you know. What do they say? 6 of one, half dozen of the other. Okay. While I'm sort of brainstorming here, is there another way to interpret f where maybe I could use, like, avoid a quotient rule and then try? So let's see what else I could do. Could I bring this x to the negative 2? I'm sorry, x to the 2. Could I bring that up top as x to the negative 2? And I can do that. I just got to be careful with the way I write it and with my parentheses. So in other words, if I read this out loud, it's x to the fourth plus 1. So let me write x to the fourth plus 1. And this is x to the fourth plus 1 divided by x squared. That's the same as x to the fourth plus 1 times x to the negative 2. Right, so if we bring it up to the top, it becomes multiplication, which means, though, I need to wrap that in parentheses. Okay, so you just got to be careful about that. Can I do that, though? Yes, that's legitimate. I'm sorry, that's not the derivative though, right? That's our original function f. I'm allowed to do that. Is that smart? I mean, as far as a technique to carry on, maybe. What would I have to do now? Now I'd have to use the product rule, right? I've got a product. So I have to use a product rule. I have a negative exponent, which muddies the waters a little bit. But I could do a product rule. So it's not really terrible to do this, but I wouldn't claim it's any easier than just using the quotient rule earlier, right? So there are multiple ways to manipulate a problem and to tackle it. They'll all work. So if you want to practice your product rule, do this, find the derivative, and then simplify it and see if you get that. But anyway, so lots of different sort of side exercises I'm exploring here. Anyway, we started with f, and now we have f prime. So let's get back to the question at hand, which is finding minimums and maximums. And I just erased the derivative, but I think it was this: 2 x to the fourth minus 1 over x cubed. Okay. So let's think back to our original function, f. F of 0 did not exist. The original function has no y-intercept. There's no point where x is 0. Okay. Let's look at the derivative. Let's just discuss the domain of the derivative. So what's the domain of the derivative? Well, I have x's in the bottom. X can't be 0. So 0 cubed is 0. That's the only value that's bad. So 0 is bad in the denominator. And as I mentioned in the previous video, or in general, the top can be 0 as long as it doesn't make the bottom 0. So for instance, 1 to the fourth is 1 minus 1 makes the top 0. The bottom then is 1, so 0 over 1 is 0. That means f prime of 1 is 0. That exists, that's fine, so that there's no problem with that. In fact, that we just stumbled on a critical number right there, right? But remember, so the points where the top is 0, we actually want to find those points, so they're not out of our domain. So the domain of this derivative is the identical set to the domain of the original function. Which in a way you could argue, I guess, is good. I mean, there's no good, bad value associated with mathematical expressions, but the derivative describes the behavior of the original function. And so here, since they are defined on the same set of values, then this original function is always being described, right? There's no sort of point where we don't know what's going on. Okay. What does that mean, though, as far as critical numbers? So this is sort of debatable. So I don't want to say it's one way or the other as far as what critical numbers are concerned, what they're going to be classified as. In other words, I'm kind of pleading ignorance here as far as what the book considers things. So critical numbers, remember, critical numbers are points where f prime of x is 0 or f prime of x does not exist, right? So we've got two types of critical numbers. So let me put it this way. It's debatable, and again, I'm sure it's not debatable if I read the book and see what they say. But let me just mention, though, should we consider, if the derivative is undefined at 0, then we want to say, well, if the derivative is undefined, then that's a critical number, right? That's one of our classifications of critical numbers. Could you argue, though, that that's not fair to consider that, since that point doesn't even really exist on the parent, on the original function? And maybe, however, so again, I don't really care what the book calls it. I want to consider that number, though. So I'm going to consider it, for my own Jesse Gavin language terminology, I'm going to consider it a critical number. However, it can't be a minimum or a maximum because the function doesn't exist there. So why do I even consider a critical number? Because just because the function value doesn't exist, the behavior might change as far as increasing versus decreasing. And so yeah, technically we're looking for mins and maxes specifically, but that gets tied into looking at where a function is increasing or decreasing. And remember, the ultimate goal is to be able to graph a function. And so where f prime of x doesn't exist, I'm going to include x is 0. And I'm going to set that up on my number line and test different intervals around that and see what's going on. So I see that you guys probably can't see that x is 0, so let me just write it. Let's get better color ink right there. But x is 0. I'm going to consider that a critical number because the derivative doesn't exist. However, it can't. A min or max can't live there. So we'll build the graph. I know I'm laboring this point. Okay, let's get back to the problem. F prime is equal to 0. So that means set your derivative equal to 0. So that means set 2 times x to the 4th minus 1 over x cubed equals 0. Now, once we find the x value, it's best to sort of go back and check mentally or just visually and make sure that that number doesn't make the bottom also 0. If that happens, we might need like a replacement theorem, right, or some kind of like 0 over 0 cancellation action happening. The reason why we only care about the top being 0 is because I can multiply like so, and now those cancel over here. So x cubes cancel, so I'm just looking at the top. But now 0 times that denominator is still 0, right? So we just care about the top. Same business, I can divide by 2. So these 2's cancel, and 0 over 2 is still equal to 0, right? So I've kind of just cleaned this up. So I'm just looking at that. This is really a difference of perfect squares, because x to the 4th is x squared squared. So I can factor this into conjugates. All right. And now this became another difference of perfect squares. X squared plus 1 is x plus 1, x minus 1. All right. This thing is not factorable in the real numbers. In other words, there's no real numbers that make this equal 0. There's imaginary numbers, I and negative I. So if you guys math majors go further and you're dealing with complex numbers, x plus I, x plus minus I, right, are conjugates of this guy. We don't deal with that though, because we're just graphing in the plane, so we don't care about those. So over the real numbers, this is irreducible, we say. Cannot be reduced, cannot be factored, so we've got that. Okay, we're equal to 0. So now let's look for solutions. Again, this is never 0 because x squared at minimum is 0, but other than that, it's a positive number. Then we're adding 1 to it. So that thing's never 0. This is 0 when x is negative 1, and this is 0 when x is 1. Okay, just visually double checking. Plug either one of those values, 1 or negative 1, into the expression. You raise them to the 4th power, they become positive 1. 1 minus 1 is 0, makes the top 0. And you cube either one of those numbers, and you're not getting a 0 in the bottom. So the function, the derivative is defined. We're good. Okay. So here, let me put x is plus or minus 1. Just kind of tie them together, right? So there's 2. So 3 numbers I want to consider altogether. Okay. Let's clear things up. Get my test line going. So I want to keep my derivative here because I'm going to be calculating things into my derivative. Let me sketch or plot my 2 critical numbers. And in a different color, again, and this I'll do red, but I'll try to make it visual. Let me plot the 0. All right, and I'm doing it in red. It's not going to be a min or a max because the function doesn't exist there. However, I believe the behavior of the graph is going to change around it, meaning increasing or decreasing, and that's still valuable information. Okay, so I'm gonna try to figure it out. So let me jump in and do some test values here. So choose something to the right of 1. How about 2? So let's say f prime of 2. And remember, all I care really about is positive or negative. I guess I could just do it all in my head, but I'll show a couple substitutions. We've got positive 2 living already out here, and then 2 to the 4th power is 16 minus 1, so I get 15. And 2 cubed is 8. And so you could calculate this 30 over 8, 15 over 4, right? We want to reduce all that if you care. But all I really care about, the result we want, is that that's a positive number. Cool. So usually I draw these little bubbles. You don't have to. This is just my style. Draw the bubbles to represent the intervals. Positive, f prime is positive. I try to be clear with my notation here. The derivative is positive. The result we conclude from that is that the original function is increasing. Okay. Eventually, down the line, we're going to deal with second derivatives. The second derivative, so you've got f prime, and you've got f double prime. So if this is positive, that tells you this is increasing, right? It's because it's sort of antiderivative, you might say, or the opposite version. But then it also tells you something about this. So the second derivative tells us different information about this and this. So just to sort of prepare for when we get there, I try to be extra clear in describing both functions and what we know is going on. All right. Okay. So back to it. Let's think about even functions, odd functions, right? I love that concept because it saves us time. If I do f prime of negative 2, well, negative 2 to the 4th and positive 2 to the 4th are identical, right? They're both going to give me that positive 15. However, negative 2 to the 8th, I'm sorry, negative 2 cubed is going to give me negative 8. Right, where positive 2 cubed gave me positive 8. So if I did this, I'm going to get 2 times 15 again. 2 times 15 over negative 8, which is now positive over negative, which ultimately is negative. Okay. Using the odd nature of this derivative, I know that it's going to be the opposite. If on one side, what odd means is the function has rotational symmetry, and so if around the origin, right? So if a function is somehow increasing over here, then when I rotate that around, this point jumps down there, and then that piece got rotated around is now, no, that doesn't sound right. That seems like that would be increasing, and then that would be increasing. Oh, never mind. So, it was getting mixed up. Yeah. I almost wanted to pause it, but we're 22 minutes in. No. I mean, the original function, so in other words, yeah, that looks increasing. We just found that the derivative here, f prime, is negative, which means f is decreasing, right? But it's the derivative is the odd function. So this graph would represent sort of a derivative here. So the fact that this line lives beneath is negative, right? The fact that this line lives above the x-axis is positive as far as the derivative is concerned. There we go. The original function is an even function, right? Because x to the 4th, x squared, both being squared, which means if you've got a point over here that's ultimately the derivative is positive, so rising, then now even functions are reflected across the y-axis. So this piece is here. And so the reflection of this increasing piece, if we move from left to right, is decreasing, right? So the derivative was negative. Mixed myself up right there, right? Because we've got the original function, which is even, and that's what we're drawing conclusions about, increasing versus decreasing. The derivative was just positive versus negative, and again, that switches if you've got an odd function with a positive function value, and then you rotate around the origin, you end up in quadrant 3, which is now a negative function value. Cleared that up. Okay. Anyway, if you're not a fan of that symmetry stuff, don't worry about it. It's covered in pre-calc, and I always emphasize while we're in pre-calc, you know, I don't really care to quiz students on positive versus, even versus odd functions just for the hell of it. It's useful though. So as students, it's useful for yourself if you recognize that you get these conclusions as freebies. So let's try to get a conclusion here as a freebie. F prime of 1/2 is 2 positive times 1/2 to the 4th power is going to be 1/16, right? So something less than 1, between 0 and 1, and you start multiplying itself, it shrinks. So you get 1/16 minus 1. That's going to become negative. And then you've got a positive number 1/2 cubed, which is positive down there, though. So here, 1/16 minus 1 is negative 15/16, and then everything else in here is positive, but that negative creates the whole result negative. All right, so f prime negative, which means f is decreasing right there. Okay, and that means what's going to happen over here? That means f prime will be positive here, right? The derivative is going to have the opposite sign because the derivative was the odd function right there. What's going to happen with that is if you did f prime of negative 1/2, you're still, when you raise that to the 4th power, you're still going to get positive 1/16. So the top is still going to become negative. But now you're cubing a negative in your bottom, and negative over negative will give you your positive result. All right, so f is increasing right there. Okay, we're done with our derivative test. Let's draw our final conclusions about maxes and or mins, and then we'll consider what the graph of this might look like. So let me get rid of the derivative now. We don't need it anymore. And I like to draw these arrows. So f was decreasing, and then it turned around and increased, right? And the function existed at -1, right? -1 was a point in our function. Let's plug it in to double verify, because we want to know the function value anyway, so we can plot the point. F of -1 is -1 to the 4th power plus 1, and then over -1 squared. So -1 to the 4th power is 1 plus 1. -1 squared is 1, so 2 over 1. So we get 2. Cool. So we got the point -1, 2 is a minimum, right? Okay, f of 1, again, using symmetry, f is an even function. So 1, positive 1 now to these powers, 1 to the 4th plus 1, 1 squared. We still get 1 plus 1 over 1. Same thing, right? So we got the mirror image over there. So we got those two values. Here, we were decreasing and then increasing, right? So minimum. Let me draw the point because the points existed. What was happening when x was 0? Well, remember, x, the original function doesn't exist when x is 0. So the function does not have a maximum, right? It doesn't have we didn't find a maximum. We found that it's increasing, and then it turns around and it's decreasing, but there's no maximum value. In fact, what is the graph going to have there? It's going to have a vertical asymptote, right? If we look at the graph, it's going to have a vertical asymptote. As we took the limit, as we approached 0 from either side, the top is growing. As you approach 0, these values are both getting really, really large. The top, we're adding 1 to it, so that's going to be a number larger than 1 divided by something that's, if it's approaching 0, it's smaller than 1, and so that ratio is going to go up to infinity, right? And because everything's positive, we're going to positive infinity from both sides, okay? So 0 is not a maximum. Important to note. Let me keep this number line. So why did I want to consider 0? Why did I want to keep 0 as a critical number throughout this process, though? If it can't be a minimum, if it can't be a maximum, why did I want to do that? Because, like I said, I might want to discuss other things about this function. So let me write this. F is increasing on 2 different intervals, right? Wherever the derivative is positive. So f prime of which is positive there. So from -1 to 0, and also from 1 out to infinity. Right, so I might want to say that, and how would I know that if I didn't test on use 0 as a critical? So I would know that I've got 2 different intervals here. Okay, there's a more important thing to think about. So let me get rid of these points for a second. Let's say I didn't put 0 on there, right? I'll leave the red mark. But let's say I didn't do that because I was like, well, the regular function is not defined when x is 0, so why, it can't be a min or a max. So who cares? Let's just throw it out and not worry about it. The problem with that is, right, we use our critical numbers to break up this number line. That's why I draw these bubbles. So if we don't have 0 as a critical number, then I'm looking at that bubble, right? The problem is the derivative, we already know the results. It's negative on this side of 0 and positive over here. And so if you don't consider 0 and you just consider this as one interval that you have to test, then if you don't pick the correct point, you're not going to get the proper result. right? So when we tested a point over here, let's say test, which we wanted to do, we found that the derivative was positive, that's why I drew this up arrow here, right? Let's say if I'm not considering 0 a critical number and I'm only looking at this interval, what if I chose a number that lived on this side, right? Then I'd plug in 1/2. I'd say, oh, f prime of 1/2 was negative. That means the function is decreasing on that whole interval, right? And that's not true. If I thought that, then we're decreasing, the graph was flat, and then kept decreasing, then I'm claiming that we've got that kind of behavior, right? And we don't, because we know that it does increase for a while. And so you do really need to include that value right there where the derivative was undefined, even though the regular function was undefined. All right. So last but not least, let me just do a real rough sketch of this graph. What did we find? We found that 1, 2 was a function value, 1, 2, and we found -1, 2 were function values, right? So we've got those two function values right there. The graph was decreasing to a minimum and then increasing. We know our function is not defined when x is 0, so we don't have a y-intercept. And so our graph was, remember it was kind of flat here, so let me extra exaggerate. Decreasing, turn flat, increase, looks like that. And then on this other side, we were decreasing, and then we flattened out, and then turned and increased. All right, and so the function looks something like that. So we got a minimum, no maximums, because every point, it just keeps going higher and higher, and no y-intercept because of our original function. Okay, guys, 2 long examples. So I thought to just do the first example, but then I wanted to tackle something like this where there's an asymptote involved. Let me know through email if you have any other questions. I'd be happy to go over some more of these, but that's probably going to be our 2 examples for 4.1.